Hello students, I am Professor Anindo Das from Achiever Circle and welcome to the lecture series on real gas, and this is real gas lecture 3. So welcome all. So in this particular lecture, we will deal with the Amagat's experimental curves and their interpretations. So Amagat did a very fundamental and legendary experiment on the real gases, and he had made some very important interpretations out of that. So it is one of the most fundamental or rudimentary experiment carried out in context to real gases. So before going into the detailings, at first, we need to have a basic idea of one of the most important physical parameters in context to real gas, and that is the compressibility factor. So, at first, we need to define the compressibility factor. So compressibility factor is a physical parameter, and it is defined as the ratio of the real molar volume to the ideal molar volume. Compressibility factor, it is defined as the ratio of the real molar volume to the ideal molar volume, and you can see compressibility factor denoted as capital Z. It is given by V bar real divided by V bar ideal. V bar real divided by V bar ideal. Okay. It has got one more definition. It can also be defined as the ratio of the real pressure to the ideal pressure. So one can also define it like PR, real pressure, divided by PID, the ideal pressure. So this is the entire expression of Z. Now, in case of ideal gas, we always have V real to be equal to V ideal. If the gas is ideal, then VR is equal to VID. Then V bar ID and is in the numerator, V bar ID is in the denominator. So both the numerator and denominator same. So Z should be equal to 1. So for ideal gas, we always have Z to be equal to 1. But for real gas, naturally, V bar R is not equal to V bar ID, or PR is not equal to PID, and thereby Z real is not equal to 1. So if Z real is not equal to 1, then you have got two options. Either Z real is less than 1 or Z real is greater than 1. If Z real is less than 1, if this is less than 1, then what happens? Then PR by P ideal, this becomes less than 1. That means PR is less than P ideal. And if Z is greater than 1, then PR by PID becomes greater than 1. That means PR is greater than PID. What does that mean? If PR is lower than PID, then some other molecules are pulling it back. So it's an attractive force. The actual pressure is lower than the ideal pressure. We have already done it in our previous lecture. When does the actual pressure becomes lower than the ideal pressure? If some molecules are pulling the colliding molecules back. The molecule which is ought to collide with the wall is getting pulled back. It's getting attracted by the neighboring molecules. Then there is an attractive force. So if the actual pressure is lower than the ideal pressure, then the force that is acting over there is attraction. On the contrary, if PR is greater than PID, then what happens? The molecule which is ought to collide with the wall is getting pushed from behind, is getting repelled from behind. So the intensity of collision becomes greater than the ideal situation. So in that case, we have repulsion. So if actual pressure is lower than the ideal pressure, attraction. If actual pressure is greater than the ideal pressure, repulsion. Actual pressure lower than the ideal pressure means pulling force, attraction. Actual pressure greater than the ideal pressure means pushing force, repulsion. Done. So, defining Z in terms of V bar real by V bar ideal, you have got Z equal to V bar real divided by V bar ideal, and we already know that P ideal equal to V bar ideal, P ideal multiplied by V bar ideal equal to RT. So V bar ideal is nothing but RT by P ideal. So we replace V bar ideal by RT by P ideal, and thereby Z is becoming P ideal multiplied by V bar ideal divided by RT. If you are defining it in terms of P real by P ideal, then now you are writing P ideal as RT by V bar ideal. Write it like that. So Z becomes P real multiplied by V bar ideal divided by RT. So either Z is equal to P ideal multiplied by V bar real divided by RT, or it is equal to P real multiplied by V bar ideal divided by RT. In both these cases, the denominator is all the same. So you don't have to worry about the denominator. But in the numerator, you see, if the pressure is ideal, volume is real. If the pressure is real, the volume is ideal. So it seems that there is a difference, but the quantity is same. So is there any fallacy with that? Answer is no. The same quantity Z has two different expressions. The denominator is same, but the numerator seems to be different. If the pressure is ideal, volume is real. Here the pressure is real, the volume is ideal. But the thing is all the same, because in both cases you have an interaction between a real term and an ideal term. Here also you have got a real term and an ideal term. So forget about real pressure ideal volume or ideal pressure real volume. Forget about that. In the numerator you have got pressure and molar volume. If one is real, the other is ideal. So you are getting an interaction between a real term and an ideal term. That's it. So we are lifting these suffixes and we are simply writing it like PV bar divided by RT. If P is ideal, V bar is real. If P is real, V bar is ideal. So it is simply written like this. PV bar divided by RT. Okay. So this is the concept associated with the compressibility factor. Now with special reference to Amagat's experimental curves, you have to answer these questions. Now what is Amagat's experimental curve? At first you have to understand this. In case of Amagat's experimental curve, what Amagat did, he plotted Z, the compressibility factor, along y-axis and pressure P along the x-axis. So the Amagat's plot is like a plot of Z with respect to P. Z is plotted along y-axis and P is plotted along x-axis. And you have got two types of Amagat's plot. The first one is a plot of a particular real gas at different temperatures. So you select one real gas, say nitrogen, and you plot Z with respect to P at different temperatures. This is type 1, which we'll be discussing now. And then you have got type 2, where you have a fixed temperature, say 25 degrees centigrade, and you have a lot of real gases, hydrogen, helium, nitrogen, chlorine, carbon dioxide. So at a particular temperature, you are plotting different gases. That is type 2. But for the time being, we'll be focusing only on type 1. Now we are not reading out these questions. Just we are making interpretation of the Avogadro's plot, that too only type 1. In that course, eventually, you'll see that we have answered all these questions. So forget about these questions. Let us just know that you have got Z along y-axis and P along x-axis. And we are focusing only on type 1, where we'll be plotting Z with respect to P for a particular gas at different temperatures. And let's see what the experiment is giving. Okay, in this particular case, in this particular question, we'll not make any explanation. We'll just note down the observations. In the next question, we will make an attempt to answer these observations or to explain these observations. But that is coming next. At first, in the very in this very particular part, what we'll be focusing on? We'll be focusing on type 1 Avogadro plot, where we'll just note down the observations, the experimental observations. So let's see. You see, you are plotting Z with respect to P. You are plotting Z with respect to P. So Z is plotted along y-axis and P is plotted along x-axis. Okay. This red line, let me make it red. This red line is the ideal line. For ideal gas, you'll have a straight line, because for all ideal gases or any ideal gas, Z is equal to 1. So at any pressure, the value of Z is equal to 1. So Z ideal is 1. Okay. Now you have got the temperatures T1, T2, TB I am coming, T3, T4. So the temperature is increasing in this direction. Temperature is increasing in this direction. Now at first let us make the observations very clear to all of us. I am not going into the explanation right now. What is the observation? For the lowest possible temperature, what you have? You have the highest downward movement. At first you have got the highest downward movement. Then you have got the highest upward movement. At first you have got the highest downward movement. Then you have got the highest upward movement. Now you increase the temperature to T2. The downward movement has been lowered a bit. The downward movement has been lowered a bit, and the upward movement also has been lowered a bit. Now what about TB? For TB, you don't have any downward movement initially. It goes along the ideal line. Then you have got just the upward movement. Then you are going beyond TB. What happens? You only have the upward movement, but the extent has been lowered. then you are increasing the temperature further, you'll have the upward movement, that to a very low extent. So what is our observation? At the lowest temperature, you have highest downward movement, highest upward movement. You gradually increase the temperature, the intensity of downward movement decreases and the intensity of upward movement decreases. Eventually when you reach TB, you don't have any downward movement, you just have got the upward movement. And if you go beyond TB, then what happens? You don't have any downward movement, you just have got upward movement, but the intensity is lowered. And if you keep on increasing the temperature, you'll just have that upward movement only, but the intensity will be lowered with every increase in temperature. Okay. Okay. So if you keep on increasing the temperature, you'll just have, beyond TB obviously, you'll just have the upward movement, but the intensity will gradually get lowered and lowered and lowered. Okay. So this is our observation. So let us jot down the observations at first. Before going into that, let us define two terms. The downward movement is known as UPD, under perfect deviation. It is the deviation from ideality, because ideal line is running straight, parallel to p-axis with an intercept equal to 1. So if you are making a downward movement, then it is known as under perfect deviation. And if you are making an upward movement, it is known as over perfect deviation. So under perfect deviation, this is basically the under perfect deviation, this is UPD. And this is the over perfect deviation, this is OPD. So for UPD, the slope is del Z del P at constant T. Slope means dy dx, y is z, x is p, so del z del p. Obviously you are keeping a particular temperature constant, the temperature is constant at T1. So del z del p at constant T. If this slope is negative, you have UPD. And on the contrary, if this slope is positive, it's OPD. So you have got UPD and OPD. If the slope is negative, you have got UPD. If the slope is positive, you have got OPD. So you have got under perfect deviation if the slope is negative, and you have got over perfect deviation if the slope is positive. Okay, so downward movement is UPD and the upward movement is OPD. Now, some very important observations has to be noted. For all isotherms, you have a common point. For all isotherms, you have a common point. You see, this is the starting point. At P equal to 0, this is P equal to 0. At P equal to 0, for all the isotherms, for all the temperatures, isotherm means for all different constant temperatures. So for all the isothermal lines, these are the isothermal lines. So for all the isothermal lines, you have got Z equal to 1 at P equal to 0. So all the isothermal lines initiate from Z equal to 1. So at P equal to 0, you have got Z equal to 1. Can you suggest any reason behind that? The reason is very simple. You can just think that if you increase the pressure, what happens? The molecules come closer to each other. And as the molecules come closer to each other, what happens? The force of repulsion or the force of attraction, which are Coulombic in nature, will increase because they follow inverse square law. On the contrary, if you decrease the pressure, what happens? The molecules move far apart from each other. And as the molecules move far apart from each other, what will happen? The interactions will decrease. So if you keep on increasing the distance by lowering the pressure, then what happens? The molecules will go far apart from each other, and thereby the interactive forces will decrease. So at P equal to 0, मान लो कि vacuum है, at P equal to 0, what will happen? At the vacuum, what will happen? At P equal to 0, you are attaining the state of vacuum. And at the vacuum, what will happen? The molecules are far, far, far apart from each other. And as they are far, 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 far apart from each other, they will not dare to interact. So although these molecules are real, they will inherently show ideality. They will inherently show ideality. Very simple. Because they are not allowed to interact with each other. Okay. So this is the situation. So at P equal to 0, Z is equal to 1. And you have got a logic. In this case, only we are noting the observations, but if we find any logic, we are writing that. Nothing else. We'll explain these stuffs in the next question. Now what happens at P tending to 0? In the low pressure region, what you will see at the low pressure region? Just focus in the low pressure region. In the low pressure region, what will have? In the low pressure region, you'll see there is UPD, UPD. Then at T equal to TB, the UPD is 0. Then you have got OPD, OPD. This is what you see. So in the low pressure region, you have got 3 layers. At T less than TB, what you find? You find UPD. And you see, as you lower the temperature, the extent of UPD increases. If you lower the temperature, the extent of UPD is increasing. Then what happens at T equal to TB? At T equal to TB, there is no UPD, no OPD. That means at T equal to TB, the slope del Z del P at constant T is 0. Z is equal to 1. Obviously under the condition of P tending to 0. I have got this. Now what about T greater than TB? You have got OPD, only OPD. Now what happens? With increase in temperature, T3 to T4, you are increasing the temperature. What happens? The extent of OPD decreases. So as we increase the temperature, the extent of OPD decreases. Okay? Okay? So, we'll make these conclusions over here. At P tending to 0, at T less than TB, you have got UPD. With lowering of temperature, the intensity of UPD increases. At T greater than TB, you have got OPD. With increase in temperature, the extent of OPD decreases. And at T equal to TB, what happens? You don't get any deviation. That means TB is basically the characteristic property of that particular gas. Like melting point at a particular pressure. Say melting point of water is, melting point of ice is 0 degree centigrade at a pressure of 1 atmosphere. That is the property of water defined at a particular pressure. Similarly, TB, which is known as the boil temperature, it is the property of a particular real gas. How come it becomes a property of a real gas? Very simple, you see. At T equal to TB, you don't have any deviation from ideality. So at T equal to TB, if you maintain low pressure, see if you are maintaining low pressure, you'll see there is no deviation from ideality. So boil temperature is the characteristic property of that particular real gas where it behaves like an ideal gas at a low pressure region. And this boil temperature will vary from one gas to another. For nitrogen, you have a particular value of TB. For carbon monoxide, you have a particular value of TB. For carbon dioxide, you have a particular value of TB. So TB is the property of a particular gas. It's the characteristic property of a particular gas. And at that particular temperature, what do you have? You have ideality maintained in a low pressure region. Okay. So you have got P equal to 0. You have done P equal to 0. You have done P tending to 0. Now P high. Last part is P high. If pressure is very high, then what will happen? If pressure is very high, then you just have OPD. You just have OPD and nothing else. And you see, as the temperature is lowered, the extent of OPD increases. For T1, the lowest temperature, the OPD is highest. For T4, the highest temperature, the OPD is lowest. So for P high, you just have OPD, and as T gets lowered, the extent of OPD increases. That's it. So these are the observations. And in this course, you have answered all these questions. Okay. Now we are moving on to the next question. Explanation of Amagat's curves from Van der Waals equation of state. This is our part C. They have asked, can you explain the Amagat's curves from the Van der Waals equation of state? So part A and part B got answered. Now we are moving on to part C, the explanation of Amagat's curves from the Van der Waals equation of state. Here we will explain the Amagat's curves from the Van der Waals equation of state. Let's check whether we can do it or not. Let's check. So this was our Van der Waals equation of state. We have already deduced the Van der Waals equation of state in our previous lecture. And we know that it is equal to P plus A by V bar square whole multiplied by V bar minus B is equal to RT. We have got this equation. Now let's make an attempt to explain it. So at first you multiply this stuff together, P V bar minus PB plus A by V bar minus AB by V bar squared equal to RT. So I've got it. Now we know that Z is equal to PV bar by RT. So you divide both sides by RT and you bring this thing here. So PV bar by RT, this is Z, is equal to RT by RT is 1. This minus sign becomes plus in the right hand side. So it becomes plus PV by RT. This plus sign becomes minus A by V bar RT. This minus sign becomes plus AB by V bar square RT. You have divided RT all throughout and you have brought this entire thing in the right hand side. So I have got this. So I've got the expression of Z. Now in the right hand side, what you have got? You have got V bar, you have got V bar square. Now you need to replace these things. Now what was our equation? Our basic equation was P plus A by V bar square multiplied by V bar minus B is equal to RT. If you write it in a single line, then you'll see that it's a cubic equation of state. If you take the LCM altogether, then this V bar square and V bar term, it will yield a cubic term. If you do the LCM and proceed algebraically, you'll see that it's a cubic equation of state in context to V bar. So if it's a cubic equation of state with respect to V bar, then we expect 3 different roots, out of which the primary root is the ideal root. So we are simply considering the ideal root V bar to be equal to RT by P and nothing else, because the other roots are very complicated. So we are not indulging the other roots over here, and we are just focusing only on the basic fundamental ideal root, and the fundamental ideal root is RT by P. So we will just use the ideal root over here. Obviously this is an oversimplification and it infuses a bit of error, but we can neglect that error. In this particular level, we can neglect that error. That's why instead of solving the entire equation and using all the 3 roots, I am just using the ideal root. Obviously, I am infusing a bit of error over here, but that error is negligible. That makes stuff simple. Otherwise, it would have been a very complicated algebraic equation. Okay, that's why I am replacing V bar by RT by P. So this V bar is replaced by RT by P. So you have got RT over here, so it becomes RT square and P is going in the numerator. And here you are replacing V bar by RT by P, and you have got V bar square, so it becomes RT by P whole square. So you have got RT whole square in the denominator, and you have also got RT term, so it becomes RT whole cube, and the P square term is coming, which is going to the numerator as P square. Simple algebraic replacements. So this eventually becomes the expression of Z in the power series of P. The first term is P to the power 0, it's 1. The second term contains a P term, P to the power 1. Here also you have got a P term and you have got a P square term. You can write it in this way, see. Z is equal to P to the power 0 plus, you fuse the second and the third term together. So it becomes like 1 by RT multiplied by B minus A by RT multiplied by P to the power 1. So I've got a P to the power 1 term plus AB by RT whole cube multiplied by P square term. So you can see we have expressed Z in a power series of P. The first term is P to the power 0. The second term contains P to the power 1. The third term contains P to the power 2. Okay. By some simple algebraic adjustments, we can do these things. Now see. See, I have infused the second and the third term together, and you can see Z has become 1 plus 1 by RT whole multiplied by B minus A by RT multiplied by P plus AB by RT whole cube multiplied by P square. So, you have got things simple. Now, let us remind what I have studied in the previous section. In the previous section, we have studied the observations. Those were coming from the Amagat's plot. And we found that at P equal to 0, all the isotherms were ideal. At P equal to 0, all the isotherms were ideal. So at P equal to 0, Z is 1. Can you explain it? Obviously. If you put P equal to 0 in this equation, what will get? All these terms will vanish and Z is just becoming equal to 1. So you can explain at P equal to 0, Z is 1. It is very much explained from the Van der Waals equation of state. Now, P tending to 0. Remember, at P tending to 0, what were our observations? If you remember, at P tending to 0, we found that at P tending to 0, we found that if T is less than TB, then you have UPD, and if T is lowered, UPD increases. At T greater than TB, you have OPD, and if T is increased, OPD decreases. And at T equal to TB, you have got no deviation. So let's see whether we can explain this thing from this particular equation or not. Now what will happen at P tending to 0? At P tending to 0, we can easily neglect, we can easily avoid the square term. It's negligible. So if we abstain from writing the square term, what will have? You have got this term only. Z equal to 1 plus 1 by RT whole multiplied by B minus A by RT multiplied by P. I have got this term only. Now at T equal to TB, at T equal to TB, you have got no deviation, means Z is equal to 1. So you substitute Z equal to 1 and T equal to TB. So Z is equal to 1. 1 is equal to 1 plus 1 by RTB, it should be TB, whole multiplied by B minus A by RTB multiplied by P. Now this 1 and this 1 will cancel out. So this term is basically equal to 0. This term is basically equal to 0. Now, P is not equal to 0. TB is not infinity. So 1 by RTB is not equal to 0. So obviously this term must be equal to 0. This term must be equal to 0. 1 by RTB is non-zero because TB is not infinity. We know that. Because we have got higher temperatures than TB. So this is non-zero. Pressure is non-zero because pressure is tending to 0, it's non-zero. So if this is 0, then B is equal to A by RTB. That makes TB to be equal to A by RB. So you have got TB equal to A by RB. This is the expression of TB. And you see, this TB contains A and B. A is the Van der Waals constant. B is also another Van der Waals constant. So these two constants bear the nature of the gas. So TB also bears the nature of the gas. So TB must be a property of the gas. You can understand that. A is the property of the gas, it bears the nature of the gas. B is the property of the gas, it bears the nature of the gas. That we have already studied in our previous lecture. So if A and B bears the nature of the gas and R is the universal constant, then TB must bear the nature of the gas. As simple as that. Okay. Now what happens at T less than TB? What happens at T less than TB? If T is less than TB, then what happens? What happens to this term, B minus A by RT? If you lower the temperature, if the temperature is TB, this term is 0. If the temperature is TB, this term is 0. If you lower this temperature, then what will happen? If you lower this temperature, then T is in the denominator. So what happens? This A by RT term increases. But A by RT term has a negative sign in front. So the value of the negative term increases. So the negative term becomes greater than that of the positive term. So what will happen? Eventually the term within the parenthesis or within the bracket becomes negative. Because at T equal to TB, this term was 0. But if you increase T beyond TB, if you decrease T below TB, then what happens? If you decrease T below TB, then the negative term increases. Then the entire term becomes negative. If the entire term becomes negative, then what happens? This term becomes negative. This is positive. This is positive. So overall this becomes negative. So Z becomes 1 minus something. Because they are adding a negative term with 1. So it becomes less than 1. So you will get UPD. So you can see at T less than TB, you have got UPD. And see, you have got a 1 by T term as the coefficient. You have got a 1 by T term as the coefficient. So if you keep on decreasing the temperature, then 1 by T will increase. And thereby the intensity of the negative term will increase. If 1 by T increases, then you are multiplying a greater term with a negative term, then the value of the negative term will further increase. Okay? So, if it becomes more negative, then the extent of UPD will also increase. So, thereby, with lowering of temperature, the extent of UPD increases. As simple as that. So, you can explain this fact as well. This fact. So, if you can explain this fact, this is coming analogically. So, if you are increasing the temperature above TB, you will have OPD. And if you keep on increasing the temperature, the 1 by T term will decrease and the extent of OPD will decrease. So, you can explain it accordingly or similarly. So, if you can explain this one, this is already explained. So, this much is explained. So, I have got P equal to 0 explained, P tending to 0 explained. Now, P tending to infinity or P tending to very high value. At P tending to very high value, what will happen? This term will predominate because it contains P square. And what is the sign of this term? The sign of this term is positive. So a high positive term will predominate. So Z will become greater than 1. This term is negligible in context to this particular term because it contains P square. And a high positive term will predominate. So Z will become 1 plus a very huge term. This is negligible. And this is predominant. So the predominant term being positive, Z becomes much greater than 1. So you are getting OPD. So that's why at very high pressure you will get OPD for any isotherm. And if you decrease the temperature, what happens? If you decrease the temperature, you have a 1 by T cube term. So if you decrease the temperature, T cube is in the denominator. So if you decrease the temperature, what will happen? The extent of this positive term will keep on increasing. And the extent of OPD will also increase. So lowering the temperature increases the extent of OPD. Okay. So in this way, we can explain all the observations, those were made by Amagat in context to the Van Doel's equation of state. Okay. So in this lecture, we have made a very important observation of Amagat's curve, the plot of z with respect to p, and from there what we did some very important interpretations, and we have explained those interpretations by using the Van Dahl's equation of state. So this was the lecture where we have dealt with type 1 Amagat's plot. In the next lecture, in the coming lecture, we'll be dealing with type 2 Amagat's plot. So stay tuned. Bye bye for now.